inches of snow, maybe 4 on Saturday, Friday, and then about 6 or 8 more. But I'll show you on
It wasn't the fringes of that.
I'm going to show you.
Radar scope. Yeah. It showed the band of heavy snow just southeast of it.
Yeah.
Just as it was. But you were much further north.
We were first one, so we came down through the St. Lawrence Seaway, across the Bay of Fundy. We were just to the east of that storm on Sunday. On the west, we were back on, and then we cut across it and got right through the woods. Okay. Okay, we're ready for our discussion. We're going to start off with our state climatologist talking about December, long delayed discussion, which we had to cancel twice now. Thanks, Pat, for coming back.
Yeah, great, thank you. I'm just very happy to finally be here. At the beginning of this year of Weather Watch, we're going to be talking about December. We're going to be talking about January, which was December, but more so. We're going to be talking about the lake ice in Madison. And then also a 2025 overview and a somewhat subjective Wisconsin's top 5 of 2025. So just jumping right into the December and January temperature anomalies. So over here on the left, we have the daily average temperature anomalies for Madison, which is largely representative of the state average as well. So the first couple weeks of December were very cold, followed by quite warm over the holidays. The beginning of January then was warm and even warmer than that warm stretch in December. And then, as you might recall, these last couple weeks, the very end of January was very cold, even colder than the beginning part of December. In terms of just the statewide temperature anomalies for the whole month of December here on the left, and then the whole month of January here on the right, actually very similar. The December temperature anomalies for the whole state was almost -4 degrees, which is the coldest temperature anomaly that we've gotten in the state since April of 2022. January was not far behind, with an average temperature over the whole state for the whole month of -3.2. So very cold months back to back. In terms of the snowfall for December, we actually had a fairly normal December. The northern part of the state got 15 to 20 inches. The southern part of the state got somewhere between 5 and 10 inches, which was just about average for December. January, on the other hand, was another story. The central part of the state got very little snow. The north got a little bit more, and us here in the south got somewhere between 5 and 10 inches, which is several inches less than normal, unfortunately. Some notable events for December and January. The cold spell, December 1st through 14th, over 100 daily low temperature records were either broken or tied for Wisconsin. January 8th, during that warm stretch, we had record daily rainfall for much of western Wisconsin, with the highest rainfall recorded being 2.5 inches. And so with January being one of the drier months in Wisconsin, that single day of rainfall accounted for more than 100% of the normal January precipitation. And so this triggered a flood watch, which was the first January flood watch in the state since 2013. There didn't end up being significant flooding, probably because the ground just wasn't frozen. We had such warm temperatures at the end of December and then leading up to this rainfall event. The soils just weren't frozen, and so they were able to soak in that rainfall. January 8th, 9th, and 13th, we had record high temperatures in southern Wisconsin, including here in Madison. And then January 23rd and 24th, it was cold. The coldest recorded temperature was -42 degrees in Knight, which is in Iron County in northern Wisconsin. Oops, and there's the video, Pete, if you wouldn't mind. Just clicking through that a couple times. So this is oh no, it's so blurry again. It might get better. Yeah, there we go. So this shows the surface air temperature. Oops, there it goes. It doesn't autoplay, unfortunately. So just a nice animation from NASA. just showing the very cold temperatures from January 21st through the 27th. Oh no, go back. So there's a couple neat things. One, I really like that you can see just the daytime temperature heating in all these just little spikes. Another thing to note too is that the white temperatures are freezing. So most of the country was, at or below freezing for a good chunk of this week, or that week. So there we go. All right, moving on to lake ice. So monitoring the lake ice is one of the oldest services that the State Climatology Office does. And so this year, Lake Winger froze on December 1st, which was 2 days later than average. Monona froze on December 12th, which was 3 days earlier than average. And then with that big warm-up in the second half of December, Lake Mendota froze on January 1st, which was 11 days later than average. And just to note that the definition of a lake freezing over, just historically, and so we've continued to use this definition, is more than 50% of the surface being covered with ice for 24 hours. And so even with the big warm-up in December and then January, a lot of the lake ice melted, but not enough to consider the lakes open. So the lakes have stayed closed since these dates. All right, jumping right into the year in review. So 2025 temperatures. The average temperature was 44.6 degrees, which was 0.8 degrees above normal, based on the 30-year climate normal from 91 to 2020, which makes us the 19th warmest year since 1895. The precipitation across the state, we averaged 30.6 inches, which was almost 3.5 inches below normal, which makes this past year the 52nd driest since 1895, and especially with this second half of the year being much below normal. Wisconsin, coming into this new year was in a lot of drought condition. All right, so the top five. So number 5, the record November snowfall for southern Wisconsin. On November 29th, southern Wisconsin got 9 to 14 inches of snow, which was the snowiest November day on record for Madison. We got 9.3 inches. The previous record was 7.5 inches on November 27th, 1995. The Madison November snowfall total was just over a foot, which makes this last November the 3rd snowiest November since 1895, which I suspect some people in this room appreciated.
Yes.
Milwaukee, too, got 9 inches, which made it the snowiest November in Milwaukee since 1995. And just looking at the percent of normal for the accumulated snowfall for November, the southern part of the state was at 500 to 700% of normal for November, which was great if you love the snow. All right, number 4, the summer smoke from the Canadian wildfires. We had 22 days of air quality alerts, which was the second most since the alerts started being issued in 2007. We had 9 days of continuous air quality alerts, which was the longest consecutive streak of air quality alerts, again, since 2007. Number 3, we had a well above average tornado season. We had 39 tornadoes from 9 storms, including 4 EF2s, which is the 6th most since 1950. The average for the record since 1950 is 23 tornadoes from 9 storms, and the record year is 62 tornadoes in 2005. Number 2, the April 18th hailstorm in southern Wisconsin. This saw hailstones being produced up to 2.75 inches in diameter, which is baseball sized. That's just ridiculous to me. And so the NWS Milwaukee Sullivan Station issued the first ever destructive severe thunderstorm warning for this storm. And then 31 minutes later issued its second ever destructive severe thunderstorm warning. And so just what does that mean? So in 2015, the National Weather Service started rolling out these impact-based warnings based on how bad a severe thunderstorm or a flood or a tornado actually could be. So for a severe thunderstorm warning, a considerable severe thunderstorm warning is one with golf ball-sized hail or 60-mile-an-hour winds. A destructive one is one with baseball-sized hail or 70-mile-an-hour winds. And so this is just what the text for one of those severe thunderstorm warnings looked like, which is just very ominous to me. At 7:04 a.m., a severe thunderstorm was located near Edgerton. This is a destructive storm. Hazard, baseball-sized hail, 60-mile-an-hour wind gust. Trained weather spotters report baseball-sized hail. People and animal outdoors will be severely injured. Expect shattered windows, extensive damage to roofs, siding, and vehicles. Thunderstorm damage threat, destructive. And then the number one for 2025 is our new 24-hour rainfall record. That has been confirmed. This was from the August 9th through 10th storm in Milwaukee, which recorded 14.55 inches of rain. The previous record was 11.72 inches in northern Wisconsin in Ashland County in 1946. Yes?
A question. It's interesting, a couple things about August 9th. One was, I think in the slide deck you were showing the period of days with hazardous air quality. And I think it ended sometime around that time period.
Ooh.
Or close to it, I think.
Let's go back.
Through the
Yeah,
6th.
yeah,
Okay,
just about.
around that time. I was curious about just the amount of rainfall that fell, because the other aspect of it was August was below normal for the state. When you were showing the numbers, the precipitation totals for each month, and you showed that August through the end of the year were below normal.
Mm-hmm.
How much of what happened in southeast Wisconsin contributed to us being just barely below normal versus well below normal? I think that was a fairly localized event.
Yeah, that was pretty localized. I'm not sure offhand. I mean, since this is an area-weighted calculation, I mean, we'd have to see. I mean, I'm sure a little bit.
Right.
Yeah, that'd be interesting to see, though.
It also points out just people's experience if they lived in southeast Wisconsin. It's like, what, August was dry.
Yeah. Not for them, but for the whole state it was. Yeah, and so with that, here's to a great 2026, and may your weather always be interesting. That's all I have.
Any questions?
Any questions?
All right, thanks, Paul. Thank you. I really like those overviews because it's so easy to forget.
So easy to forget what happened. You know, I mean, I was at County Stadium, well, whatever it's called now, AmFam Field, on August 9th, and it was raining like I've never seen before. Then we had that heavy snow in the end of the month, and I remember the November 27th, 1995 storm too. So I've seen two of the snowiest days ever in the state's history in November. So it's been great.
Right. Also, the other thing is, just remember, when you showed the first part of January being above normal, it's like, that's a blur.
Yeah,
Everything that's
absolutely,
happened
yeah.
Since the middle of January through now.
Yeah, really true.
Yeah.
So is it one full week, Pete?
This is a week, yep.
Yeah.
The beginning of it starts last Friday.
Been really active in the Western Atlantic. And some of that activity's been sampled by the field program that I'm involved in, and Professor Lang and Flora are out today, I think flying. They're both on the plane today. Out of Goose Bay, Labrador, which is right there. I landed there on Thursday, the 22nd of January. It was minus 21 or 22 degrees. Then we had 2 or 3 days that were in the minus teens. And then, and I broke my all-time record. I now have 111 straight hours at a place of residence, defined as, did you do laundry there? Which I did once. 111 straight hours with temperature below 0 Fahrenheit. And it broke, my other record was here at 98 hours or 100 hours in February of 1996. So I just barely broke it. I was hoping to get to minus 30, but the pattern was so progressive, and it still is. With exceptions, you know, these things get wound up in the Western Atlantic, and then they race across right now. They're not kind of going up to Greenland and Iceland. And so no really deep cold air was able to sit there and get colder on site. And so I thought that was the only chance to get to minus 30. But it hasn't happened. So that's still, my record is still minus 28, and that was here in Madison. So it was really exciting. Pete, can we slow down and stop on February 1st around 18Z?
ETZ the first.
Yeah. The only time I got to go on the plane was to sample this event. So the cyclone, at the center of the cyclone, right here off the Virginia-Carolina coast, I think it was about 970 millibars or so, something like that. And we took off, we were supposed to go on Friday and sample this thing the 2 days earlier, but we got canceled because we got to the runway and the conditions had deteriorated in just the 25-minute taxi from the hangar to the runway to cancel the flight. Saturday was a deep snowstorm. We had about 8 inches of snow, which was great. I got movies of that I'll show sometime. And then Sunday dawned with some mystery, but it kind of cleared up enough that we got out. And so the plan was to fly from Goose Bay straight through we were just to the west of this island, Anacostia Island, I think it's called, in the St. Lawrence Seaway, right through the Bay of Fundy, and we started sampling right off the southwest coast of Nova Scotia. So we had a sonde here, a sonde here, a sonde here, and they were in the backbent warm front portion of the cyclone, and it was fabulously interesting. Low tropopause, beautiful veering with winds through the frontal structure. Then we got down to here and we went straight across. We got into this clear air. We had 3 sondes there and then a couple more going back to Goose Bay through the warm front. It was on its way out in terms of intensity. Had we gone on the Friday, we would have seen it even more intense, I think. But the soundings were fabulous. One of the great things about getting right there at the right time was that there was all these dying anvils. You could see that they were decaying. And what was left underneath them was cumulus congestus. And from 41,000 feet, it's difficult to tell what's going on underneath. You're waiting to see the sounding data come back. And we were able to see in real time that the winds were in the 65 knot range, mixing ratios of 11 grams per kilogram in the boundary layer, and wind speeds in the 65 knot range. I might have already said that. And then when we finally got through the clouds, it was a little bit hazy, but you could see on the ocean surface what looked like little specks of rice. And it dawned on me, those are whitecaps. And those were whitecaps of probably 30-foot seas. And they were confused because they were back on the western side of the storm. So they weren't all coming in the same direction, as you might imagine if it's just an open fetch. So the fetch was being pushed in a whole bunch of different directions. That would have been absolutely the worst place in the world to be, on a craft, at the surface. I'm sure there was 80-foot mountains of water that were breaking in what we determined was a sea salt haze, because we could see with another of the onboard instruments, which is a depolarization ratio of a couple of different wavelengths of radiation. And the experts on board were able to tell me this. It was like having a seminar. We're going to have Amin come here and give a seminar on this because he's just fabulous. But 2 kilometers deep, the object he suspected was doing all the scattering was sea salt. So all the congestus was raining like crazy. We had an onboard radar, the Cloud Cube radar, which is just like the CloudSat. I mean, not the CloudSat, the CubeSat, but it's on board the aircraft. So we're seeing it rain like crazy out of these shallow congestus clouds, and they're pumping all of the sea salt from the breakers into the air, and then they're immediately evaporated at about 2 kilometers, so all that's left is the sea salt. So there's just sea salt haze through which we're seeing these whitecaps. Fabulously interesting. So sometime in the next several months, I hope to be able to show you some of those observations from just that one flight. We've now had 9 successful research flights in this project, and this was the first one that really interrogated the structure of cyclones, so I was so glad to be on that one as opposed to one going off over one of these small tropopause polar vortices that we hope is where the forecast said it was. There's no mistaking where this thing was, so we were right in the heart of it, and it was great. We did get it a day too late. I would have loved to have gotten it in more of its vigor, but it was still majestic to be flying through this thing. So anyway, that's just one of several storms that's kind of wrapped up. We can keep going forward, Pete, thanks. That's wrapped up on in the Western Atlantic over the last several days, and the project has been the beneficiary of that. I'm not sure if it's just a lack of weather or if it's something about a football game, but Sunday is a hot down day up in Goose Bay, so they're all going to take that off. The main pilot is from Seattle, so we had long conversations about Seattle sports, and he'd love to see the Seahawks win, which so would I. I mean, that would be great. A lot of my friends are Seahawks fans. But a very interesting project, and we deploy again next winter, and hopefully the broad scale picture will be a little different. Right now it's really kind of breaking ridge on the west coast, which forces northwesterly flow over us, has kept us chilly, and lots of little disturbances can develop there, but many of them end up too far south out of the current flight range. Next year we have a 777, so we can go vast distances. We can go like 10 hours away from Goose Bay if we're there. We may even be in Bangor, Maine instead. So anyway, we might be able to catch some of these upper frontal structures, which the TPV people, they're talking about all these little cold spots on the tropopause as if those are the things that drive cyclones. They're part of an environment that evolves on a much bigger scale than them, I think, in most instances. So I got to try and bend the curve a little bit on that as time goes on. It would be interesting to talk to Andrea when she gets back, because I think she'll have the same view as I do, and Andrew Winters. So fabulously interesting project. And at the end of the current satellite loop, you can see there's some interesting things going on here on the border between Ontario and Quebec in the deep cold air. So this cyclone here on the southern end of James Bay, there's the swirly. That was earlier in the week, sorry, not the same one. So there's another one coming. Where is it now? Maybe I was thinking of the wrong thing. No, there it is, that's the one. That's a decent storm that's kind of up there. And this skirt right here is just cold air, it's not cloudy. And you'll see that in a couple of other depictions. That's just cold air on the west side of the storm. So it's a really nice wintry satellite movie that we're looking at right here. A lot of cold air funneling down off the continent into the Gulf of Mexico. Huge amounts of heat and sensible and latent heat exchange. Let's take a look, Pete, if we could, at the, because we want to go kind of quickly here and make sure we get through everything. Let's take a look at the current, not the current satellite, we kind of covered that. Let's look at the radar composite.
Matt Hitchman chimed in online and really enjoyed your flight description.
Oh, excellent. I hope that when I get the soundings out and try and put it into some context, it'll be even more interesting. Probably it won't, there's no chance it won't be, I suppose. This is all precipitation associated with that troughiness to the east of a big anticyclone that's sagging southward over southern Canada and the northwestern Great Lakes states. Most of the region here is snowing. I think it's even at high elevation in the Virginias, it's snowing. Probably not snowing in this down here in the valley in the central part of the state of Virginia, but we'll check that in the obs in a minute. I know it's snowing up in these locations. Some places in eastern Ohio today had heavy snow for a period of time. So this is an interesting local and quickly moving event. They had 22 inches of snow in Boston, the storm before the one I sampled, and that second one looked like it might be the second pulse of really heavy snow. Even Halifax looked like it was in the sights for 22 or 28 inches of snow, and it all moved a little bit further east and began to fall apart. So not quite the threat that it looked like at one point. But that's the only sensible weather going on across the country today in terms of precipitation. And you can see it's fairly contained, regionally widespread, but not particularly well organized. Let's take a look, Pete, at the surface maps just to follow this up so we can see how much of that is snow. I think most of it is. So we saw all the way down into the Virginias, moderate snow in the mountains of West Virginia, moderate snow here in, where is that, Knoxville or someplace? Oh, that's Tennessee. That's Louisville. So,
No, you're right.
No.
It's Kentucky.
Yeah, it's Kentucky. I forget what town it is. There's no snow in the Carolinas, but there's snow in Western Virginia, in West Virginia itself, light snow in Pittsburgh. And there, as I said, not true anymore, but there was some moderate snow in some of these stations in the eastern part of Ohio.
Yeah, those dew point depressions in central and eastern Virginia are pretty large for.
Oh, yeah, they are. 36 over 14, 30 over 14. Yeah, it's hard to. And where it's snowing, it's 32 over 25. So is that Blacksburg?
Roanoke, I think.
Oh, Roanoke. And so that's the end. It's not going to snow anywhere else. And dew point depressions are almost nothing where the moderate snow is occurring. But even there, 3-degree dew point depression. Okay. And we're enjoying spring-like temperatures here today. 36 degrees is magnificent. It just feels great.
Just wait.
Bring it on. Okay, let's take a look at some of the upper level charts if we could, Pete. We'll start with the Epinema Super, Pete, at 500 maybe. So here's this morning's 6 a.m. 500 millibar chart. And this is the consequence of having this kind of constant ridginess over the western United States, is that we can dig out cold air from the far northwestern part of the archipelago, slide straight southward across the continent. And there hasn't been, to my liking, as much development along this northwesterly transect as I would like. Sometimes these things can become really potent upper vorticity features. And then the one that spawned the storm that occurred, the one that we sampled, was quite like that. It was a really intense upper vortex, swung around, came off the coast of Georgia and South Carolina, and developed this really intense cyclone. As a consequence, dragged mixing ratios of 11 grams per kilogram up from the subtropics to the Maritimes, and we sampled that. But there doesn't seem to be too much development, at least at this stage, in this particular example of northwesterly flow. A little bit of a shortwave trough here, more impressive at lower elevation. That's the one that's tied to the developing cyclone here in southern Hudson Bay. That is an exception. That's a fairly exceptional feature. But this little thing here, under other circumstances, could be more impressive itself and perhaps dig a substantial trough off the East Coast. It doesn't appear that it's going to do that. So here, fairly innocuous at 500 millibars, a little ridginess over northern Manitoba, and then the trough over the Hudson Bay in Ontario cold air advection and cyclonic shear, dropping the tropopause likely in Western Ontario. Let's see what it looks like at 700 millibars in that same location, since that's a place where there's some cyclogenesis. Substantially more impressive looking, wouldn't you say? So low heights here on the west coast of James Bay, very intense geopotential height gradient, and very strong cold advection with a very obvious leading edge right over northern Lake Superior and on the border of Minnesota with Western Ontario. So that's the beginning of our cool down, which is going to come this weekend. So that's an impressive feature in the lower troposphere. Notice at 700, no such thing to the south. So it's really that one that's developing now. I don't know if we're sampling that thing in the project. I kind of doubt it. And let's go to 850. I think we see even more of the structure of the frontal zone associated with this. Yeah, so here's a pretty low geopotential height, smack dab over central part of James Bay. Minus 31 is the coldest analysis temperature, but the coldest ob is minus 25 at 850. That's pretty cold. Here's the leading edge of the cold advection at 850 millibars. It's just now across the border into our own state. Bayfield is probably the first recipient at 850. So at the surface, it's probably about here at 12Z. Yeah. So we're going to be feeling that by the end of the day today. And that's a pretty good chunk of cold air. Notice it's exhausted by the time you get to this point, and it's not any colder to the north. This is it. But it's substantially colder than we are right now.
So nothing but a barbed wire fence between us and the North Pole?
That's correct. Maybe some hay bales if there are some animals out there trying to make lunch out of what's going on in the prairie provinces. But most likely it's just barbed wire. And strong northerly flow goes right through the barbed wire, bringing very cold temperatures to us. Let's go to a hemispheric perspective if we can. Oh no, Pete, 300 millibars first. I don't want to show the hemisphere. So here's the 300 millibar map, same time, 6 a.m. this morning. There's a relatively warm pool at 300, so this is deep in this lower stratosphere. Then on this side is upper troposphere. 151 knot jet, and it's right about in this location, of course, where there's a bit of a troughiness that we have the cyclogenesis. So it's somewhat divorced from the jet. Certainly, its position relative to the jet has nothing to do with the exit entrance regions. It's kind of squarely at the same relative position of the jet as the core of the jet. So it's not really driven by that. But it's an intense jet, and there's slight hints of cold advection along at 500 millibars, which sometimes induces strong trough development in middle and upper tropospheric levels. As I said earlier, I don't think that's going to be the case in this instance for whatever that reason might be. Why is there no particular concentrated region of cold advection and cyclonic shear? That's a research question in and of itself, case study type research question. Okay, so let's take a look at the hemisphere. I want to show you some interesting things. I might maybe go to my password. I don't like it. Okay. So let's see, what should I use here? Oh, you do? Okay, great. All right, so you know I keep track of this cold pool at 850 millibars. Here's the time series all the way through yesterday, February 5th. And this turns out to be the warmest all time from December 1st to February 5th. So we started becoming warmest all time by about mid-January. And so we are on track. We only have 23 days to stagger to the finish line and be the warmest December 1 to February 28th of all time. Brad?
Do you just do that as like the integrated area over the season? Is how you check that?
I do the departure for the day from the daily average, and then add them up for 90 days. And whichever one ends up with the biggest negative number has the biggest integrated departure. So it is what you think, it's an integrated departure from average. And we're sitting at the warmest, smallest integrated departure area of all time, 1948 to 2026. So this is pretty interesting. What I've done too is I've said, okay, we got this far into winter. Then let's figure out what is the warmest February 6th to February 28th of all time. And what does that time series look like? Because that's what we need to, if we replicate that, then we're definitely the warmest of all time. So that year was 1997. And this dashed line indicates just February 6th to February 28th. That integrated departure period was biggest in the negative side in 1997. So we could still afford an excursion above 1 standard deviation below the mean, but we'd have to go way down here to be like 2 or 3 standard deviations below the mean to equate this kind of warmth for 1997. I don't know if that'll happen, 23 days to do it. The warmest year of all time was 2013-14, and it actually also ends up being the second warmest, February 6th to February 28th. Yeah,
Is this just in Wisconsin?
I'm sorry?
Is this just in Wisconsin?
No, this is the whole northern hemisphere at once. So the whole northern hemisphere at once. For those who have not, I kind of just glazed over that. What I do is I find where's the -5 isotherm at 850 millivolts, about a mile above the ground. And then I figure out how much area is contained by that isotherm around the whole hemisphere. And it grows during the winter and it shrinks during the summertime. And so I compare the area on any of these winter days to the historical average on those winter days and so on. And so that's what I mean, warmest all time. It's for the whole northern hemisphere at once, which is awesome. 2014 was the second warmest, February 6th to February 28th. And it has many of the same features. There's still room for an excursion of cooling in the hemisphere and some warming, but we just got to stay well below the average to finish out the year on top, which I would love.
So John, for this time, and what was the other, 1997?
Yeah, 1997.
At this date, where did those rank?
That's a good question. I don't know about this one. This one I think was second of all time at February 5th.
Okay.
And by something like 25 million square kilometers or something like that. 2.5 million square kilometers, which sounds like a lot, but it's not. It's the size of half of Greenland. So this one is the closest competitor. And also, maybe it got to be #1 currently as it is because it had such a warm end to winter. I don't know that. That's an interesting question. But if we can get something like this for our time series over the next couple of weeks, we're in like Flint. #1. So you always want to win. You always want to win trophies. This is the trophy that I'd love to get.
But with that area being over us, or the lack of area being over us, after this winter, I'm ready for warmth. So,
Well, this is warmth. This is testifying to it around the whole hemisphere.
Look what we've experienced.
Yeah. Well, that's the other cool thing about it is I show this. I'll probably show this at some talks to the general public at some point in the spring. And I'll say, remember how cold it was at the end of January? We were way above average for the hemisphere. And I'll say, what? Well, that's the difference between climate and weather. You know, where you are and the whole hemisphere is different. But yeah, so I'd love to get there. If we do, then 3 years out of the last 12 would have been record-breaking warmth by this measure. Because we did it in 14, 15, 13, 14, and then we might do it in 25, 26. And so that's amazing. When you're running in a street where 25% of the time you land on an all-time warm record, it's probably likely that something's going on in the background. Whether or not you believe it or not is not really important. It's a fact. So that's kind of cool, what's going on there. So I'll keep you up to date. I don't want to bore you next week, unless I have bad news, I'll tell you. But if we don't have any bad news, I'm going to keep this surprise for a couple of weeks so we get right close to the end. All right, that's all I have. Oh,
Okay, we're going to get started. I wanted to go back a week. Unfortunately, for good reason, didn't have our weather watch last Friday. But we would have been talking about this fairly impressive trough that was just crossing through the Wisconsin area at this time. John's already alluded to sort of the future of this trough, its future evolution. And let's actually just step through this at 500 hectopascal on superheats over every 12 hours. So we can see this trough as it's moving southeastward. And we can just step ahead one more time. You can see its tilt, so-called tilt, is beginning to change, becoming almost neutrally tilted. At the same time, there's anticipation, and we'll stop right there for just a moment, of a fairly impressive cyclogenesis event occurring just off the East Coast. Now, there had been talk in the days preceding this event of maybe a major snowstorm of up to 2, maybe 3 feet, impacting parts of central Virginia, central Maryland, through the mid-Atlantic into the Northeast. But over time, it became clear that this was going to be an event that focused mostly on the eastern part of the Carolinas, maybe southeastern Virginia, where in fact some of these places, in fact also western North Carolina, got somewhere on the order of about 20 inches or so of snow. So a pretty impressive event. It did in fact become a explosively deepening cyclone out in the western Atlantic, deepening well over 24 millibars in 24 hours as it exited the East Coast and deepened. And that's, I guess, the cyclone you sampled part of.
Yeah, and they were
at a later
talking about
stage.
this as instigated by a tropopause polar vortex that we looked at in eastern Hudson Bay 5 days earlier, but it's too simplified. It was part of the environment, but it wasn't the whole thing.
Right.
Yeah.
So if we keep clicking just a couple more clicks, you can see this becomes a fairly broad, vast upper trough as it moves out, but really intense cold air advection at 500 hectopascal over the eastern part of North America and then into the western Atlantic. And then this eventually fell apart. But if we go back to the beginning of this, again, just to really, I don't think we can go any further back, right? The first time we have is the last time we have. Is that correct, Pete? At 12Z on Friday last week?
Yep.
So really intense trough. And one of the things that that I like to do is look at sensitivities of cyclogenesis events to sort of upstream initial conditions, or just the initial conditions in general in a forecast model. We'll look at that in a second. But I also just want to look at, Pete kindly saved both some satellite and radar loops of this event. First, I'd like to start with the water vapor imagery, upper level water vapor loop.
Yeah, I know the 1990s called, they want their webpage back. It works.
Hey, that looks like my webpage.
Hey, it works.
That's right. That's right.
It's old school. All right. So here's the trough. As it, we'll stop at 12Z just to reorder ourselves. One of the really impressive things, you can see the dry air in the upper troposphere, indicated by these blue areas right here. But here's our upper trough. Also would be associated with an area of enhanced potential vorticity in this upper trough. Okay, and we can also see sort of a surge of moisture, water vapor across the southeastern, from the eastern Pacific across the southern part of the United States into the southeastern United States. Well, let's just follow the progression of this trough over time. Again, we saw that in sort of discrete steps every 12 hours on the super piece, but you can see the drying that's occurring in here as the tropopause fold presumably is beginning to develop. And you'll begin to see during this time period sort of a blossoming of clouds just off the southeast coast of the United States. Not this area so much, but look at this really dry air here.
Yeah.
But the cyclone's getting going. This is now early on the 1st. This huge blossoming area of cloudiness and actually precipitation we'll see on the radar at this point. Here's that upper trough sort of becoming cut off, and then we see the cloud head beginning to develop around this developing cyclone. You can sort of see the gyrations in the cloud as this cyclone
That's
really
what we
begins to
get
take
into
off.
right now.
And then this moves into the far western Atlantic. Really impressive storm. Let's go back and look at the visible imagery that you have for this.
Any preference on
This is square root. Because why not? So this is the visible imagery on Friday evening, just before things really start to get going. Sun comes up, and we can see the cold air just streaming southward, but really the development of this cyclone, just here, you can just see the edge of it. Unfortunately, it's nighttime. I can see much.
Oh, look at that.
But look at that really impressive cyclonic circulation of the clouds, the low clouds, and really this cold air just streaming off the continent. It's a really impressive storm. Maybe we'll look at the IR imagery. Pete, we'll see if we can stop after this.
the cold air in the Gulf? We got a report online that Cuba got their first 0 degrees Celsius on record.
Really?
Oh, with this event? That's impressive.
On February 3rd.
Okay. Let's go back.
That's amazing.
The IR loop, where's that first one? And just one other view of this. Again, these are some clouds that are streaming ahead of the upper trough as it begins to dig southward. But, you know, a lot going on in this image, and I haven't really begun to sort of unpack the full sort of measure of all the elements that contribute to the storm. But this initial blossoming of cloudiness, really deep clouds just off the southeast coast before the arrival of this upper trough that I think is of interest. The so-called barochromic leaf cloud that often begins to spread ahead of a developing wave is also impressive. You have this one, but you also have this second one that develops, and that's where the cyclone center begins to develop as it drifts northward or northeastward. And again, this time they're getting some pretty significant snows in the eastern Carolinas. There's that warm core disturbance moving out to the northeast.
Yeah,
A little bit of convection developing north of it.
my sense of why this thing didn't quite come to the level that it looked like it might is that it's just too progressive. Somehow there's no ridge building.
Okay,
upstream,
all right.
In spite of all the heating.
All right, yeah, this is okay, I'm excited about this because this is, we talk about these things so much.
Yeah.
This is really interesting. So one of the things that really got me, and I would have hammered this on a week ago, was when all this talk of a big mid-Atlantic snowstorm. One, you need heavy snow and you need it to be for a long period of time, so it has to be a slow-moving storm. What was missing? The big anticyclone to the north was just lacking there. Having an anticyclone to the north would have helped contribute to, with the cyclone to itself, to stronger, warmer advection, which could have actually increased the diabatic heating and helped build a much more impressive ridge here, so that it would have been less progressive, it would have been slow moving, and you wouldn't have gotten the snow there.
Yeah.
In fact, there's some elements, can't show them today, maybe I'll show them continually over as I'm sort of developing my thoughts on this particular case, that when we look at sensitivities to cyclone intensity, there is some evidence that having a decrease in the potential vorticity and increase in the amplitude of the ridge downstream of this would have led to even more intense cyclone. This was already intense, but it could have been even more intense, and that also had implications on how it moved, how it propagated. So the next thing I want to show, thanks Pete.
Professor.
Yeah.
Something, I was forecasting for that storm a little bit beforehand, and what I had noticed, you mentioned with the cloudiness out in front of it, that was not directly associated with it. If you looked at some of the other, maybe more surface fields, that developed a low farther off the coast underneath that convection. I think it just caused the whole thing to be a little disorganized.
That's also, I think, a fair comment, and I think there's some elements that we can see in that. And looking at some of the surface maps from some of the model output during this time period, it did show these cyclones attempting to develop further to the east, and the whole system kind of got dragged back to where the upper vortex was, and in a region that would be favorable for development. But there are probably multiple really small-scale cyclones developing in this. And yes, I'm talking about a mid-latitude cyclone, John. Just
I
so
know. I
you're aware.
can tell by the excitement level.
And this will be it for the year. All right, so I've had my fill on that. So let's quickly
You
show
don't have
one
to
image.
wait weeks for the next aborted attempt at a cyclone like you do in the tropics.
Well, that's what makes them so special, John.
Well, I guess if you keep plugging that potty line, it makes you happy. That's good.
Okay, so before I cook things up. Okay, I'm soaked up. So what I did was, this is using the WRF model, did a simulation of this event starting at 12Z, the map time that we showed earlier, with the upper trough, cleanly shown here. And I asked the question, in the forecast, it was a 48-hour forecast. Cyclone was developed roughly in this box. By 48 hours, it would have been contained in a box roughly like this. And I'll show more of this later on. So the question that I was asking is, how could we have created a much more intense cyclone in that box at 48 hours if we perturb the potential vorticity, in this case, the quasi-geostrophic potential vorticity? You want to increase it, decrease it, and where would you want to make those changes? That's number one. One thing that's interesting about this event was, in fact, that in that box that I selected, there was the main cyclone. It was down at 970.3 hectopascal. The 0.3 is irrelevant. But there was also a sort of a weaker cyclone, or a very long inverted trough that was pretty baggy to the northwest or northeast of that cyclone, which is consistent with what was just reported. So choosing that box was a little bit tricky. But the end result of this, doing the calculation, running the adjuvant model backward in time, and then post-processing that output to look at sensitivities to potential vorticity, that's what this shaded field indicates. And so the way we interpret this is, if we wanted to deepen the cyclone 48 hours later, at the time the model was initialized, which is this time, at 500 hectopascal, we would want to have put more potential vorticity near the tip of this trough over parts of the Dakotas into southern Minnesota, and along a line that was just perhaps north of us and decrease the potential vorticity downstream of that trough. In fact, intersecting part of this little appendage to the this trough axis that goes into the northeast. So decrease the PV here, increase it upstream. Creating this PV gradient right here would enhance certainly advections of potential vorticity. But this indicates that some aspects of this trough could have been perturbed at the initial time to lead to a more intense cyclone 48 hours later. So let's advance just one slide ahead. This is the same calculation from the same run, same scaling, that shows the sensitivity. This is 18 hours later. So in the same forecast run, just as sort of actually a weak initial cyclone's already begun to develop just off the East Coast, you can see this trough that runs all the way back through Tennessee, that it still indicates a focus on amplifying the southern part of this, or the extreme tip of this PV. Well, this is a geopotential minimum, but if you were actually to increase the PV that's in this region, and I suspect if you calculated the QGPV, you would see that there's a local minimum along this trough axis. That southern piece being intensified would lead to a much more intense event. And then some other features over Oklahoma in this jet that would be favorably configured to help intensify the cyclone. So this is just the early stages of just something I'm thinking about with this storm, also testing these tools and cleaning them up. But it'd be interesting to see this, and I'll sort of, over the course of the semester, share some further work on this.
I think that's great, and I'm looking forward to seeing more. I think the interesting thing, in addition to making the already troughiness more troughy, is making the almost absent ridge more ridgy.
Right.
That's key.
And I wish I had saved the imagery for later times. Even after the cyclone developed, I think in the last 3 hours, we could have gotten more bang out of the buck in terms of intensifying the cyclone, because this positive lobe was roughly here, cyclone was here, and then the idea would be decrease the PV to the northeast of the cyclone, which really decreases the wavelength of the geopotential ridge, or between the trough and the ridge downstream, which would increase infections, lead to a more intense cyclone.
I was going to ask you if this was a subset of your domain, because I was wondering.
This is the whole domain.
Okay, I was wondering if there's anything to the east that was influencing it, but now when you get to the next, you get 18 hours into it, it looks like, no, it's all related to the structure of this trough.
Right, and the subsequent structure of this absent ridge.
Yeah.
That's there. So just early stages, but I thought it might be interesting to have a conversation about this event over the course of the semester as this case is sort of looked at a little bit. Okay, let's go now to my favorite set of maps. Still haven't corrected that dew point meteorogram yet. I actually did work on that in Python, believe it or not, so not Jetpack. It works well, but I haven't fixed it. Let's go to our meteorogram first. And I want to show you a video before we get to that. Or I'll show you, we'll get to a video in a second. I just want to say this is probably the most disturbing. It's just rude. Now, I'm talking about stuff from the White House this morning. I'm talking about the cold that's about to come in. John was talking earlier about, this weekend will get colder. No, I think we've already seen our high temperature for the day.
Yeah, probably.
And things are heading down in a big way. So here's this is the time series of our temperature and the model forecast, the WRF forecast from this morning, initialized using the NEM model. You can see that's the peak temperature for the day, and it just gets cold, brutally cold later on tonight. It'll be as cold as it was earlier back in late January, type of cold. And then temperatures tomorrow beginning to warm up. We get into the upper 20s, or the low 20s, maybe a little bit warmer than that. And then they're sort of relatively flat. When you go to Saturday night to Sunday, we'll have some clouds and maybe a little bit of light precipitation, snow in this case. If you go to the time height section, I'm just going to watch the time. The time height section, here you can see the PV structure that's just passing by us this morning. You can see the relative humidities, things beginning to dry out. The isotopes sort of bowing upward underneath this PV anomaly. And they say sort of well balled up. This is going to be cold air over us for a while as the cold advection sort of deepens the layer of cold air over us. And then you get a period of fairly intense warm advection. The column over us begins to saturate later on tomorrow afternoon. And that leads to perhaps a period of perhaps a little bit of light snow tomorrow afternoon and evening.
Oh, it's perfect.
And then, we're done with this.
No.
Enough of this. And then we begin a slow warm-up. But one of the interesting things is you'll see in this, and we'll look at some other vertical profiles, not cross sections, soundings, model soundings. Really intense stable air. We still have snow on the ground. So, John, you want to say it?
Yeah, foggy.
Fog and cold, right. So I think that's going to be one of the things that keeps us, if we didn't have the snow on the ground, and if we could mix out this really intense stable air that's indicated by the closely spaced isotopes, which are in yellow, right? That's really strongly statically stable. It's preventing lots of mixing from occurring. If we could mix out, frankly, we could be near 60 degrees. So that's how rude this weather coming up is going to be. Today was warm. It was nice out there. You didn't have to zip up your coat about an hour, hour and a half ago. But that's it for us.
Yeah, that's it.
All right, let's go quickly look at the, so where's the rude image. I'm going to go first to the 850 loop of temperature over the Madison area. And it's rude because one thing, when these were created over 25 years ago, these scripts were written over 25 years ago, believe it or not. We put a limit on how cold 850 was going to be. We reached that limit pretty quickly. Look at it, here's the cold air coming in. So goodbye to our early spring that you'll see. If you can stop the loop at the beginning, Pete. Go back to the beginning. And just step maybe. All right, cold advection at 850 has already started. As John was saying, this is in the first 3 hours of the event. The really cold air is up to the north, and again, you can't even see how much colder it is because imagining something colder. Now, this might be as we're using scripts for the warm season. I haven't updated that, but that's on me.
Oh, that could be.
But I think Darryl would have probably figured that out a long time ago. But look at this. You can't even see how cold it's going to get. In fact, I guess you don't want to know. You're trying to just forget about it.
Yeah. Yeah.
Cold advection comes in, and then it's just uniform. As John was saying, there wasn't much between us and well far to the north in terms of any temperature structure. If we go to the surface loop for the same period, you can see that cold air coming in as well.
And that's because the sun's up now in a lot of those places. You just can't manufacture it anymore. The factory's closing
The cold,
down.
the cold air, right. So this is earlier today. This is at 3 hours in the forecast when it was relatively pleasant outside, maybe the low 30s. And then here's the cold air, cold advection really starts up here. And again, 850, we already have some of the cold advection. That's probably why we've gotten a little bit of some cumuliform clouds forming. The ground warmed up, but upper levels were already beginning to cool off. And then it just gets much colder further to the north, minus 12, minus 16. And these are in degrees C. And that cold air just begins to come in, and temperatures plummeting during the afternoon. Lake effect snowband sets up on the eastern shore of Lake Michigan, but we're just plain cold. And then as you watch this loop, you can see the warm advection begin to start as these winds begin to veer a bit, becoming more out of the, I guess we can't see it on this map fully, but this is where the warm advection is beginning to set up. And we're getting light precipitation forming as the warm air tries to surge back over us. I think this broad area of precipitation might be a little bit of an overstatement. I think it's just we're close to being saturated. So certainly a lot of clouds around, but with the warm advection really trying to take over when we get into Sunday evening. Go back a few more clicks. Then we get warmer finally after that. Okay, let's step even further back. First, we'll go to the PV loops. And let's look in the lower troposphere, 305 to 315K. So we didn't really have a really robust upper PV center that came by us. It was sort of a glancing blow. If we can go back to the beginning and stop that and just step through the loop, please, Pete. All right, so this upper trough has moved over us, and we're getting the last vestiges of it as it begins to move to the east. You can see the low PV advection coming in behind it. This moves out to the east, and so that cold air is still beneath the trough. And you can just see that, again, trough slowly moves eastward, and we have this broad ridge that begins to set up over us. This comes by, well, it goes over Michigan, so that's not going to be too much of an issue. And this is where the isotopes are sort of outcropping into the topography out to the west. But again, broad ridge over us, so relatively dry weather after we get that little bit of precipitation. And let's step back.
That little cutoff over Baja California. Go forward a month, and that's a severe weather threat in Texas.
Yep.
It's a little early now, but it's the beginning of that season.
Yeah, I think in some of the forecasts a week ago, they're looking at, and we'll see this actually in the forecast for later this week into next week, or later next week into the following week, big broad ridge over the southeastern part of the United States. So it makes room for some of these southwesterly flow events and maybe cutoffs coming in, enhancing the severe weather risk. All right, let's go to pivotal. And we'll go to, let's not look at Northern Hemisphere, go to national, click on this. Let's go to surface map in 48 hours, please. In fact, I should go to 36 for just a second. I want to just check on one thing. All right, with that warm advection spreading in, notice at least in this forecast, and we can step ahead a few clicks. One of the things you'll note is this doesn't really produce as much precipitation as the WRF model did. There's a little bit of snow there, but again, I think the widespread nature of what we saw is probably not going to be realized as what the WRF is showing.
It's pretty uniform warm advection if that's the only dynamic, so that's positive reasoning.
Yeah. So that's, okay, and we can step forward, maybe just go ahead every 24 hours. You can click on from 72, let's start at 72. So this looks promising, right? You have warm advection, so you think, oh, we're gonna warm up, but if we were to just do a sounding right here, it's just frustrating.
Yikes.
This is incredibly frustrating. One, close to being saturated. Okay, if we could take this air and just bring it down dry adiabatically to the surface, we're about 58 or so, right? Of course, we can't do that because we have the strong stable layer.
10 megaton nuclear device to do that.
Right. It's going to be a struggle, even with that strong warm advection, those high thickness values. Remember, thickness is an average temperature, so, or as a measure of the average temperature in the layer, we really have to, the layer is warm, but the near surface layer is really cold. I think if we were to just change this to the NAM, which historically it does do a pretty good job, if we change this to the NAM model output, it does a good job with these cold layers. Let's see if that's also the case in the NAM, or do we get some grace from it?
Oh yeah.
Not much.
Double it.
Yeah, so again, but it could even be warmer. 21C, can you imagine that?
70 degrees. Right?
Yeah, right, yeah. 71, 68, just 1.1.
Just 21.1.
Yeah.
0.55.
Okay, so we're going to be really, so this is going to be the state for this week. Is there anything that can be disruptive to change this up a little bit? I don't really think so. It's going to be a slow slog to get really warm. Let's get back out of this, please, Pete, and go ahead to 96 hours. Oops. So nice warm thicknesses, but we're still going to be, unfortunately, not so warm. In fact, we can just do one more sounding this time. This is Tuesday. Well, it's not 20s, right? At least we got into the mid-30s. But again, this is the potential warmth that we get is just, it's tantalizingly close. But I think cloudy and just kind of gross. Okay, let's, in fact, we're at the 30s. Let's go ahead another 48 hours to 108. Not much. In fact, it's begun to cool off just a little bit, all off at that time. And back to the maps. But for this week, it looks like decent weather, but not as warm as you would hope by just looking at the thicknesses. In fact, by the time we get to Wednesday, the cold advections started again, the fronts pushed through. But that actually helps mix things up a bit, so that'll be good. Dry things out, and then we keep going to this time next week, 168 hours, warm advection starting again. So a relatively dry week coming up. The warmth, if you want warmth, go 2 miles up. You'll be pleasantly surprised. Welcome that, but at the surface, it looks like we'll probably stay close to freezing. Maybe we might get mid-30s or so, but it's not going to be as warm as it looks by just looking at thicknesses. But spring's on the way, so just hold on. Anyway, thank you for your attention, and great to start back with Weather Watch. And welcome John back. Thanks, Pete, and thanks to the State Climatology Office.
Yeah, thanks everybody. That was a good discussion.